deenolate. And so here we are back to, or we have another case that we've already encountered now a couple of times where we have an unfavorable equilibrium, but the minor component of the equilibrium reacts with whatever other reagent is floating around in solution. Selectively, the major component does not react in the equilibrium as such, and it siphons off the equilibrium. The only twist here is that indeed the enolate that's formed reacts with the excess starting material that's floating around. So this, once it's generated, is surrounded by an ocean of this. And so it will attack it, okay? Can't help it. And so this is the next step where you get nucleophilic attack at the carbonyl function. And you kick out this electron pair, and this is also an equilibrium. This equilibrium now lies slightly to the right, but it's still an equilibrium. The lone pair kicks out, and here's the new carbon-carbon bond. Let me draw it like that. And then, since you are in water, the O- gets protonated. And you're kicking out hydroxide, regenerating the hydroxide catalyst. To give the intermediate aldol adduct. And at low temperature, you stop here. Okay? It doesn't go further. At higher temperatures, that's where the delta comes in, and that's why if you want to run it all the way through, you just run everything at high temperatures. There is now a step where hydroxide comes back in. And that last step is the elimination of water. Now, this is an unusual step, so I grant you that. This is not what you would have expected and could have predicted. Normally, going back to chapter 8 and 9 and 11, I guess, remember we dehydrate under acidic conditions because we want to turn the OH, which is a lousy leaving group, into water, which is a good leaving group. And in this way, through E1 mechanisms, we make the double bond. Or we turn the OH into a good leaving group, like a halide or a tosylate, toluene sulfonate or something like that, which then can eliminate by E2 mechanisms. Here, this is not what is required. It's not necessary because this base can deprotonate the H next to the carbonyl again. So we're now pushing this further by deprotonating again. Remember, this is a relatively acidic hydrogen. Again, the equilibrium lies mainly on the left, but this gives you the corresponding carbanion. And this carbanion then kicks out the hydroxide. And this lies way to the right. So we're kicking out hydroxide to make the product. This elimination of hydroxide is very unusual. This is actually only the second case where we have hydroxide as a leaving group. Remember, we drummed into you in 3A, hydroxide, never a leaving group, terrible, because hydroxide anion is a very good nucleophile and a strong base. So it doesn't leave. Well, there are exceptions. It leaves, or maybe one should rephrase this, it's being kicked out if there is a negative charge next door that needs to be satisfied. So we have a very bad situation where negative charge is very unhappy, and it removes itself, as it were, by dumping itself onto the OH to make it OH minus. So making, which is not ideal, but it's not as bad as where you started. Okay? That's the reason. The only case where we've seen hydroxide leave before was in the oxidation step of the alkyl borane oxidation to give alcohols. I showed this briefly last week, I think, where a migration occurred and hydroxide was kicked out. So it's very rare, let me put it this way. Notice that this is not an E2 elimination. It doesn't go by E2. Remember, E2 is where you pull off the proton at the same time as the leaving group is leaving. It's concerted. Okay? And it's an anti-transition state, if you recall, chapter, what was that, 11, I think, right? And it's not E2 because the OH really doesn't want to leave. Okay? So it waits until a full negative charge is being built up next door, and then the pressure to leave becomes unbearable, as it were, and the hydroxide is being forced to leave. Yes? I didn't get that. Why is the hydroxide? Why does the hydroxide not attack which hydrogen? This one? Because that's an sp2 hybridized aldehyde carbon. What you get then is a very bad species, right? So you can't do that. But it reminds me to drive home another question that was actually very well placed. In both of these mechanisms that I've done today, there are several occasions where you may have asked yourself, why does it attack here? I've done this bit before, actually, but I'm repeating it. Why doesn't it attack here? For example, hydroxide could in principle attack here. Why doesn't it do that? And the answer is it does. Everything that you can imagine actually occurs. But all of these reactions, if you follow them through, are dead-end reactions. And they're all reversible. So hydroxide attacking here to kick out the electron pair makes O-. This is done under aqueous conditions, so actually protonation can occur. What is that? That's the hydrate. And yes, all carbonyl compounds in basic aqueous solution are in equilibrium with the hydrates. But at the hydrate stage, they can't go anywhere. Okay? So they just go back. So that's a dead-end equilibrium, I call it. Okay? That doesn't lead to product. It's a background reaction, often called. So it goes in and out, but then every now and then it will deprotonate here, and that will cause the elimination. Another thing that this guy can do, looking at what else is floating around here, is, of course, deprotonate the OH. That's actually a very rapid reaction. That's just proton jumping between two oxygens. Okay? And that gives you back this species here. So that's on the way back to where we came from. And that's why we write equilibrium errors. So that doesn't lead anywhere. It just goes back. Okay? So the mechanism I've written is the one that leads to product. And so deceptively, and in the 7th edition of the textbook, we're now rubbing it in marginal notes frequently in all these mechanisms. Yes, in fact, there's another reaction that, of course, also occurs but doesn't lead anywhere. So I'm trying to dispel the notion that things, for some reason, don't happen when they should happen, which makes you feel very insecure. I can completely relate to this. Okay? You see a mechanism and say, yeah, I understand why this A goes to B, but why on earth didn't it do this? Because we just learned this 30 pages before, okay, that things attack here. And as I said, the answer is everything happens, okay? But all these reactions are reversible, and so in the end, the thermodynamically most stable component wins. Okay, so we got a movie on that. Aldol condensation. So here we go. Hydroxide comes in, pulls out the proton to make the enolate. Very few of these molecules float around in the presence of a large excess of starting material because this equilibrium is uphill. And so there's the surrounding unreacted aldehyde, and this guy attacks to make the alkoxide first, and then you protonate. And that's what you get is the aldol addition product. Typically, we don't isolate that if we don't want it, but rather we warm up. And this deprotonates in another position next to the carbonyl, makes a new enolate, and the enolate then kicks out hydroxide. Yeah? I can't hear you. Is it regio? What do you mean? Stereospecific, yes. It gives you the sterically least hindered compound. So in this case, it's trans. Okay? Cis is less stable than trans. And if you can't decide because of the additional substituents, you get a mixture. Okay? So back to what I've already really alluded to. If you want to do what's called a crossed aldol or hetero aldol reaction between two different components, you have to do it stepwise, making an enolate and pick the better enolate. If they're the same, then it doesn't matter, but sometimes one enolate's better than the other. And then add the other component depending on which way you want to couple. Okay? Because if you do this under catalytic conditions, so you have two, let's say aldehyde or two carbonyl components in your pot, then they will just all react randomly. Okay? So here I'm attempting to couple acetaldehyde with propanol, and out come four products. Because the propanol can act as the enolate anion component and add to the carbonyl, that gives you this compound. Or the acetaldehyde can be the enolate component and attacks the carbonyl of the propanol, and that gives you this compound. These are all isomeric. Okay? So you get four isomers. Or, these two are isomeric. Or the enolate of acetaldehyde can attack itself. In other words, another molecule of acetaldehyde. We just did that in this mechanism here. That gives you this compound. Or the two propanol molecules can react with each other in aldol, and that gives you this compound. So you get two diastereomers, not diastereomers, two isomers, positional isomers, constitutional isomers in the first two modes, and two additional different compounds in the other modes of attack. And roughly, since looking at the bond strengths, these bonds that are made and the bonds that are broken, they're all very, very, very similar. You would get a statistical mixture, very likely, of 25% of each. Okay? If you want that, that's okay, but otherwise, that's a loser. Okay? Now, the way around that and still use catalytic conditions is to carefully pick your components. And one trick, which shows up in lots of exams, is to have one component be a non-enolizable aldehyde. In other words, an aldehyde that has no alpha hydrogens, and therefore cannot be an enolate component in the aldol. Here's an example. Benzene carbaldehyde, or benzaldehyde. This carbon here has no hydrogens. This can't possibly be an enolate component in the aldol. You can mix that with an aldehyde that is enolizable and can make the enolate, and then you get properly the aldol condensation product. So those tricks are certainly possible. Otherwise, if that's not there, you have to resort to a stepwise reaction. So far we've talked only about aldehydes because they are more reactive in the aldol reaction. And in fact, as I mentioned here, indicated by these arrows, the initial aldol addition step for aldehydes is actually exothermic, slightly exothermic. Reversible, but the equilibrium lies slightly to the right. That's not something you could have predicted. It just turns out to be that way because aldehydes are more reactive than ketones. And it just turns out to be that ketones, because they're more stable, the equilibrium actually shifts now to be endothermic. So that when you take acetone in the presence of base, and this can be measured by NMR, you get the aldol addition product, but it's an equilibrium, and the equilibrium lies now way on the left. And you can measure the ratios by NMR because you can see both species in the NMR spectrum. So this is actually a measurable amount of the minor component of the equilibrium. In many cases, where we've been talking about unfavorable equilibrium and so forth, the higher energy species is then such small concentration, you can't even detect it. But by NMR, you can detect pretty much down to 0.1% by appropriate blowing up the spectrum and integration. Here it's 6%. Okay? So here, this looks useless, except that the next step, the dehydration, is sufficiently exothermic that this equilibrium is driven all the way to product. So ketones still function as components in aldol condensations. But you can't make the aldol addition products. Or you can, but you can't isolate them because they're in an unfavorable equilibrium. But if you just want to convert that all the way to the alpha beta unsaturated ketone, that's perfectly fine. So, as usual, and you can see we are now in a routine where there is an intermolecular reaction. Frequently there is an intramolecular version, and that is also true for the aldol condensation. And remember, intramolecular reactions are always faster and favorable, easier to do because primarily for entropic reasons. And so here we have an example where we take this 2,4-pentane hexane dione, and we treat this with sodium hydroxide, and out comes this 5-member ring. And how does that go? Well, you can see that the way this functions is we've got two carbonyl groups. One of them has to be the enolate component, the nucleophilic component. So every now and then, sodium hydroxide will pull off this proton, make the enolate, and then this negatively charged carbon, bang, attacks here, kicks out the electron pair, you get the aldol adduct, and then you eliminate water, and you get the 5-member ring. So at this stage, you may ask, well, the way I've drawn this arrow leads to product. That's okay, but this is an unsymmetrical ketone, right? Except that the right half is the same as the left half. But there is a metal here that we've used to deprotonate and to lead to product. What about this guy? This CH2 is about as acidic as the CH3, as the CH3 protons. So why doesn't it deprotonate here and attack the carbonyl? And the answer is, and now you can guess, it does. It'll deprotonate on both sides. Okay? But when it deprotonates here, when it attacks the carbonyl function here, it forms a three-membered ring. And so that aldol addition product is way more strained than the product that you're forming, which is a five-membered ring. And everything is reversible, so it goes in. In fact, it goes in rather fast because three-membered ring formation, as you may recall from chapter 9, intramolecular Williamson ether synthesis, three-membered ring formation is actually among the fastest, in part because of the proximity effect of the functions. But in the intramolecular ether synthesis, the reaction is irreversible. It's not in equilibrium. It just goes forward, and the molecule is stuck in the strained ring. Here, it's reversible. So it goes from here, goes in, makes a three-membered ring, and then it goes back. And whenever it deprotonates here, it can lead to a stable entity. So this is still a relatively symmetrical compound. What about cases where the two carbonyl functions are completely different, where the right half is different from the left half? Then, in fact, you have 4 different possibilities, because now this, that, and that position, they're all different. Okay? And so here's an example of that scenario. Okay? Here we got 2 carbonyl groups, and it's this dione. You boil this up in aqueous sodium hydroxide, 90% only one compound, when in fact, in principle, you could get 4. And that, again, is dictated by the fact that the equilibria leading to the other 3 lead to strained intermediates and or products. And so since it's reversible, all these equilibria are set up, but it will weasel its way into the most stable product that's possible in the mixture, 90% as reported in the literature. So how does this form? It forms by taking this methyl CH, making the enolate this way, attacking here, and then you kick out the electron pair, protonate to make the hydroxy group, the aldol adduct, which is this without the double bond and an OH here, and then you eliminate water by the mechanism that we've drawn here. Okay. The other 3 alternatives are the other side of this carbonyl, namely here. That enolate also forms, and it can attack here, and it will attack here. And you notice that when it does so, it forms a 4-membered ring. 1, 2, 3, 4. 4-membered rings are way more strained than 6-membered rings. So this goes back and forth, and it's a dead-end reaction. Then we can also form enolates derived from this carbonyl. And so let's start with this one. This is the alpha position to the top of this carbonyl. It can make an enolate this way, which can now attack this carbonyl. So the 2 carbonyls trade places in their electrophile, nucleophile acting capacity. And so when you have a negative charge here, it can attack here. Notice that that also leads to a 4-membered ring. 1, 2, 3, 4. If you make a bond, you get a cyclobutanol. Okay? That's reversible. That's a loser. And here's the last possibility. You can go over here, make the enolate this way, and that guy would then have to attack here to kick out the electron pair and form an aldol product this way. That is more difficult to see, okay? And that's not something I would have asked you to predict. Okay? But that, as it turns out, forms a bridged system. You may be able to see that because once you make a bond from here to here, this piece here becomes a bridged arrangement. And that is inherently also more strained than a 6-membered ring. 6-membered rings, remember, are the best. They're the least strained of all the rings. I'm generalizing now, but that's a good rule of thumb. Whenever you have a choice to make a 6-membered ring, that's really a winner. And so I can show you this also in a model. And again, I urge you to build your own models. And you can see that the mode of attack is between the 2 atoms I'm holding in my hands. Here's the methyl of the dangling carbonyl. You make the enolate over here. This carbon then attacks over here. And that makes a 6-membered ring. Okay? The alternative, this carbon making the enolate over here, attacking. I don't dare to even bring it closer because my bonds will snap. Okay? But you can't go from here to here. The second alternative would be to use this carbonyl as the enolate. So if my left hand grabs the carbanion from the enolate going here, we would have to attack here. And that also makes a 4-membered ring. And so the last option, which is not so easily seen unless you make a model, is this one, where you make an enolate over here. So the carbanion is here, and it attacks this carbonyl function. And you can see this is tricky. Okay, you have to bring this guy across to here. It can be done, but it may snap my model. I don't want to do it. But you can already see in the transition state that's already, or approaching the transition state, that's already not too good. Okay, let's have a break.